Okay.
Welcome, everyone. Welcome to the Queen's Observatory Open House. Thank you. All right. So this is our biggest observatory open house ever. It's the first time we've done it on Facebook. Thank you all for coming out. So those instructions up there tell you what your ticket is for, and I'll get to that after the talk. But first, before we start the talk, we're going to have a couple announcements about some science outreach activities. So if Liz could come up first, tell you a little bit about this camp.
Hello everybody, thanks for coming out tonight. I'm here on behalf of the Department of Physics, Engineering, Physics and Astronomy, the Faculty of Arts and Science, the McDonald Institute, as well as Snow Lab. Oh, sorry. And I'm excited to announce an exciting event we'll be having this summer. So it's Girls Camp. So it's a physics-focused day camp that we'll be running this summer at Queen's University for girls who are currently going into grades 7 to 9. The goal of the camp is to explore physics topics while giving our campers a strong female role models to look up to. So we'll be covering topics in physics from light and sound to astronomy to robotics. It'll be running from July 22nd to 26th. If you or anyone here you think might be interested in this camp, please check out our website. It's at the bottom here. Or come to talk to me after the talk. I'll be in the McDonald Institute Visitor Center. Thank you very much.
Thank you. Next we have a quick announcement by Susan from the Royal Astronomical Society. Here you go.
So this year we're doing a trial raffle to raise money for outreach. These are the things that we use our outreach money for. We're providing okay. So this is our beginner's observing kit. Binoculars, tripod, the 3 books, and the planisphere. The tickets are going for $2 each or 3 for $5. We'd really love to break even. So if you want to buy a ticket tonight, I have tickets here and I'll be hanging around after the talk to anybody who wants them. So if you go off somewhere else, you could stop by here again and pick up a ticket. Thanks.
Thank you. Day 11. It's going almost all day, and that's also the next observatory open house. So it can be a fully packed day of science for you if you come out. We will also be there at the Science Rendezvous, so you can check out our booth. And as a final announcement, the observatory open house now has its very own logo. So let me reveal the logo for you. There we go. That's done by Zach from the McDonald Institute. He's a great graphic designer there. All right, now on to the main talk. Here we go. Building a better radio telescope. So Kristine Spekkens, our speaker tonight, she is an astronomer. She's gone through quite the career, starting at Queen's University for her bachelor's, then Cornell, then Rutgers, then the Royal, not the Royal Astronomical Society. No, she went to the Royal Military College, RMC. That's where she is now, cross-listed with Queen's. One big thing, she is the science and engineering advisor, science and engineering design advisor for the Square Kilometre Array, which I'm sure she'll tell you a lot about today, because that is the big part. That's a big part of her work, and that's a big part of this talk today. So thank you, and please join me in welcoming Kristine Spekkens.
Can you hear me? Yeah, awesome. All right, so today I'd like to tell you about building a better radio telescope. But to start, I'll show you a picture of the night sky, the optical sky, and let's be honest here. You guys aren't all here to see me. You guys are here to go up to the roof because for the first time in a long time, it is clear outside, which is awesome. And so, with any luck, we're going to see a picture, or we're going to see stars like this in the sky, and it's going to be beautiful. It's going to be dark. So I am going to try and be short so that we can all get there. And the kinds of telescopes that you're going to use tonight, and the kinds of telescopes that you probably think of when you think of the word telescope, that's certainly what Google thinks of, because this is what you get when you Google, is a telescope that looks like this. And this is the kind of telescope that you would use to look at the kind of sky that I'm showing you right now. But it turns out that there's a lot more than meets the eye here in this picture to the universe. And if we look at different light at different energies with a different kind of telescope, we can learn all sorts of different things. And so that's what I'm going to tell you about today. So when you Google, you might get a picture like this. This is clearly a telescope. But this is a telescope. And this is a telescope. And this is a telescope. And this is going to be a fabulous new telescope. And I'm going to tell you about it tonight. So in this talk, I'm going to show you a mix of artists' impressions and real pictures. And because the artists are getting really good, I'm going to try and tell you, every time I show you a picture, I'm going to tell you on the bottom right here whether this is an artist's impression or a real picture. So this is an artist's impression of the square kilometer array. We'll get to it a little bit later. This, on the other hand, is a real image. And so I'm going to do this both with telescopes as well as with some of the images of the night sky, objects in the night sky that I'm going to show you. All right. So let's go back to this picture of the optical sky, okay? And so you can see a constellation here. And it turns out that almost everything that you see when you look at the sky with your eyes at night is the same kind of object. It's an object that's this. What is this?
The sun.
The sun, right? And what is the sun?
A star.
It's a star. Okay, so this is a picture from an observatory. It's actually a space mission. It's called the Solar Dynamics Observatory. And one of the things that they're trying to understand is how activity in the sun affects space weather. And this is a real image of the sun. And the sun is a star, and almost everything that you see in the night sky are stars. So if we go back to these pictures, in fact, a lot of these stars are more massive than the sun, but they're all the same thing. So when you look up in the sky at night with your eyes, or with the telescopes that we'll use tonight, what you see are stars. In fact, they're stars that are relatively close to our sun. They're all stars in our own galaxy. But it turns out that there's a lot more than meets the eye in the universe. So this part of the light that I showed you here, right? This is called optical light. It's the light that we see with our eyes. And the light that we see with our eyes is a really small slice of all the light that exists. And so this is called the electromagnetic spectrum, which is a terrible name for a talk in front of people wanting to go up to a telescope. But the point here is that you have light that has much higher energy than in the optical, and light that has much lower energy than in the optical. And energy is correlated with wavelength, and so this is the wavelength of the light. But we can learn lots of different things about the universe by looking at different kinds of light. So all of this is light, and when we look up at the sky with our eyes, we see only a very small part of what's there. And so what I'm going to tell you about today are some of the things that you can see if you look at the universe at radio light or radio waves. So this part of the electromagnetic spectrum. And so the point here is that radio light tells us about the universe too. And it turns out that radio waves relative to the light that we see with our eyes, the wavelength is longer, the energy is lower, and that means that we can manipulate the light in really interesting ways to give us really cool pictures. I'm going to tell you a little bit about that too. So this is a picture of the radio sky. And at first glance, I mean, there's some weird looking things here. And we're actually not going to talk about the weird looking things. I want to talk about the boring things on this plot, because it turns out that the boring things on this plot are really, really cool. Because the things in this picture that look like stars aren't stars at all. Okay? And so I can take one of these pictures, these objects. It turns out these things are really, really far away. And I can look at an analog that's very close to to our own sun. And it looks like this. And in order for me to explain to you what this is, I have to back up a few steps. Okay? So let's look at a nearby galaxy. And so this is a galaxy that was looked at with the Hubble Space Telescope, as well as with the Atacama Large Millimeter Array. And so this is a spiral galaxy like our own Milky Way, and we're going to look in the very heart of that galaxy. And when you look in the very heart of that galaxy, you tend to see a bunch of gas and a bunch of dust, and it's in a ring, and it's going very, 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 very fast around the center. And inside that torus, and inside this dust disk, is something that up until very recently we had never seen. Okay? Do we know what's in the center of? There's a hand up there. What's in the center of every galaxy, we think?
Black hole.
A black hole. So we think that if we could look deep enough inside a galaxy like this one, inside our own Milky Way, inside every galaxy in the universe, we can see a black hole. So this is a real image, but up until recently, we've never seen a black hole. And so this is an artist's impression of what a black hole looks like. And most people have probably heard the words before, but basically a black hole is an object that is so dense that light can't even escape. And the radius, or the distance from the center of the black hole within which light can't escape, is called the event horizon. And it's pictured here by the artist as black inside. And the reason for that is that light is the thing that carries energy in the universe. And so if light can't escape, energy can't escape, then no information can escape. And information is the thing that we would need in order to understand what's inside a black hole. So black holes, we think, or this artist, has assumed that this black hole has an event horizon. And the black hole's density is so big that it bends both space and time around the event horizon. And so you can see in this picture, very far, or relatively far from the black hole, you can see the space kind of looks normal, the way this artist has drawn it. And then as you go closer and closer, stuff gets kind of weird. You start to see all these arcs. Okay, that's light from behind the black hole bending around it. And if you were to see a spaceman fall into this black hole, he would get slower and slower and slower as he falls, okay, because his time is different than our time. And up until very recently, this is about as well as we could do with black holes, in the sense that we have a theory devised by Albert Einstein for what black holes look like. But they're so small in space that they're very hard to see. So this black hole and its event horizon is sitting in the center of a galaxy, and around that there's this disk of material. And the stuff around in the disk of material is falling into the black hole, and when it does, it heats up as it falls. And part of that material, or part of the energy that's generated when that material falls in, is emitted in this stream of particles here, up and down. So this is another artist's impression, because we don't have a lot of these to look at. And so these are called jets, and they come from the material, or the energy that's generated by material falling into a black hole. So you still don't see anything inside the black hole, but because this material is really hot, we can actually see it if we look close enough. So let's go back to this picture, and I'll walk you through what you see when you look at the radio sky. So we take this galaxy that looks like the Milky Way, we go into its very center, and we look near the black hole. And the black hole is at the center of this dusty, disky thing. And as material falls into this black hole, energy and particles get streamed away, probably perpendicular to this disk in a jet. And then I can take this picture and shrink it down tiny, tiny, tiny. In fact, it's tinier than this when I put it to scale, but I was worried you weren't going to be able to see it on this projector. And now I can put this picture back up. And so what you're seeing when you look in the radio sky, one of the things you see, in fact, most of the things you see are called quasars. They're distant radio galaxies where their brightness in the radio is coming from jets that are emitted by massive black holes in the centers of those galaxies. So this is a combination, again, this is a real picture of a quasar or an active galactic nucleus nearby, so it's nearby enough that we can get a picture of it. And then this is an artist's impression in here, and up until recently we hadn't looked that far down, or at those small scales. So the radio sky is mostly quasars, massive galaxies and black holes at distances that are 5, 6, 7 billion light years away. Okay? And the point here is that radio light probes a different side of the universe from visible light, so you learn something new when you look in radio waves as opposed to visible waves. I'm ignoring her because she's my daughter.
Yeah, that looks like somebody painted it.
It looks like somebody painted it, but it's a real image. So you're allowed because they're your kids, even when you're doing talks. Okay. All right. So let's talk a little bit about a telescope. So a telescope is a light bucket. So think about a bucket that you put out in the rain. Okay? And the bigger the bucket, the more rain you're going to collect. And so the bigger the telescope, the more light you're going to collect. Okay? And once you've collected all that rain, you might want to know how much rain fell on any given day, and there's lots of ways you could do it with a bucket. If you want to get all fancy schmancy, you could use a rain gauge, okay? And so once we've collected all the light, we need some way to measure it, okay? And in the optical, that's pretty obvious. In fact, all of our cell phones have something in them that measures light, that takes pictures. What is it? It's camera, right? So when you take a visible light picture, you use a camera. Now it turns out that your phones also have something that measures radio waves, and we'll get to that. But it occurred to me that as I was putting this talk together, that we don't see a lot of these anymore. And what is this? Yeah.
An antenna.
It's an antenna, right? And back in the good old days, cars and televisions and all sorts of things used to have antennas, okay? And now they're smart about the design. And an example of that is your cell phone, right? Your cell phone has an antenna in it because it receives radio waves from the nearest cell phone tower, and it's built in, so there's not a big thing sticking up. If you're old enough to have an old school phone, or to have seen a picture of an old school phone, or to have been to a museum where they have old school phones, first you flip it open, then you put the antenna up, right? Okay, so antennas measure radio light. Okay, so a rain gauge measures how much rain is in a bucket, a camera measures visible light, and antennas measure radio light, or radio waves. So if we put all this together, radio telescopes are simply light buckets that feed radio waves to antennas. So here's one example of a radio telescope. The bucket is a dish, okay? And the antennas are actually, they're kind of hidden. One of them, there's a pair of them up here, and then there's a bunch of them down here, and we often call these receivers. But that's what a radio telescope is, and I should say this is a real image. This is one of the dishes of the very large array down in New Mexico. All right. But it turns out that you can build some telescopes without dishes at all, without light buckets. In other words, what the light bucket does is it funnels light down onto the antenna. But sometimes the signal is bright enough that you don't need the light bucket part, right? There aren't dishes on our cell phones because the antenna in our cell phone is powerful enough to receive the signal it's trying to listen to. And the same thing is true with some radio telescopes. So we'll go back to this picture that I showed you at the beginning. This is a radio telescope called the Murchison Widefield Array. It's in the outback in Western Australia, and it observes at such low frequencies where the sky is really bright that you don't need a dish at all. All you need are the antenna parts. And so these antennas are spread out in clusters all around the desert or all around the outback. And they're trying to look for signatures of the first star, the impact that the first stars had on the gas in the universe. Okay? And so sometimes you don't need the dish at all. But oftentimes you need a dish. And at radio waves, you can build really, really big dishes. So this is currently the largest dish in the world, the largest telescope in the world. It is a radio telescope. It's called FAST, the 500-meter aperture spherical telescope. It's in the jungle in southwestern China, and as the name suggests, this dish is 500 meters across. So this is an actual picture of FAST. These are cars right here, and this is a road right here. And to give you a sense of scale, 500 meters is the distance between here and the biosciences complex. So imagine a dish that's the size of the distance between here and the biosciences complex. It's enormous. And if you think about telescopes as light buckets, in the same way that you collect a lot of rain if you have a really big bucket, you collect a lot of light if you have a really big telescope. And so this allows us to see really faint things in the universe. But sometimes, and one of the pictures that I showed you before wasn't of one telescope, but it was of a bunch of different telescopes. And you've probably seen this picture before. This is the full, or most of the dishes in the very large array. If you've seen the movie Contact, this is the one where Jodie Foster, I can guarantee you I've never seen an astronomer with a convertible, but apparently she had a convertible and she was flying if you're trying to listen for aliens. So this is again a real image. And what I want to tackle is why you would build a radio telescope with lots of separate dishes, because it turns out that it allows you to manipulate light in a really interesting way. So let's talk about what happens when instead of having just one telescope, you have two telescopes, two radio telescopes, and they're on different parts, they're spread by a certain distance. And if you think about the light that's coming from a distant quasar, that light, if the quasar's over here, that light's going to hit this telescope over here before it hits this telescope over here. And if you have a clock that's good enough, and you know the distance between your antennas, or your dishes, then you can measure the difference of the time of arrival of the light to this telescope and this telescope. And if you can measure not only how bright the light is, but the time difference between when those light waves arrive, it turns out that you can reconstruct an image. But what's really cool about this technique is that you can reconstruct an image as though you had one big telescope that was the diameter, or that was comparable in size to the distance between those two telescopes. So imagine that you didn't have one bucket collecting rain. Imagine you had one part of the handle over here, and one part of the handle over here, and no bucket in between, but you can still collect some rain. Okay? It's really cool, and we can do that with radio waves. And so telescopes like this are called interferometers, and they rely on this technique. And it turns out that because of the properties of radio waves relative to visible light, the energy is lower and the wavelength is longer. This technique is a lot easier to do when you're looking at radio light compared to optical light. Okay, so one of the things that for the experts in the audience, it turns out that it's much easier to amplify radio light than it is to amplify visible light, and that's a big driver behind this technological difference. And so what you have to do to make one of these things work is you have to record light from all of these different telescopes and then multiply the voltages together. And it turns out that Canadians are world experts in building radio signal multipliers. They're called correlators that make these interferometers work. And in fact, Canadians built the correlator that's the engine of the Very Large Array. One of the best, we have some of the best technology on the planet for building these kinds of machines. So we've got this technique called interferometry where we can take different telescopes that are physically separated one from the other. If we record how bright the light is that hits them and when the light strikes them, then we can use that to reconstruct an image that mimics what you would get if you had a really big telescope. So let's dream big. Instead of putting the telescopes one beside the other, like in this picture, let's put them all over the planet. Let's put some in North America. Let's put some in Hawaii. Let's put some in South America. Let's put some in the Southern Pole. And all of these telescopes make, we can correlate the signals from all of these telescopes and get a telescope that's the size of what? The Earth. The size of the Earth. We can make a telescope by manipulating radio light that is the size of the entire Earth. And so this is one of the telescopes I showed you before, and this is actually part of this array. It's called the South Pole Telescope, and so, hence the snow. And it's a telescope that works at millimeter wavelengths, so sub-millimeters. But it uses the same kind of techniques that I talked about before, and it's this telescope right here. And so that's what astronomers did very recently. They waited for a day where it was clear on the whole planet, okay? And they observed simultaneously with telescopes from the South Pole all the way up to North America and in Hawaii and in South America. Okay? And what they were trying to measure something very specific. Okay? And so this telescope was called the Event Horizon Telescope. So what do you think the Event Horizon Telescope might be trying to find?
Black holes.
A black hole, remember black holes have event horizons, right? So let's go back to this picture of the spiral galaxy where we look very deep in the heart of that galaxy and we see a dusty disk of gas and dust rotating around the center. And then the artist's impression of what that might look like if we could actually see it. So here's the black hole, this is the event horizon of the black hole, and here's the dusty disk around it, and this is so small that we've never ever seen it. In fact, you would need a telescope the size of the Earth to see it. And that, this week, is what we did. Of a black hole. And we did it with a radio telescope the size of the Earth. And it's in a galaxy far, far away. It's in a galaxy that is 55 million light years away called Messier 87. It's in a nearby cluster of galaxies. And what you're looking at here, that black spot in the middle, is the event horizon of the black hole. And up until now, nobody knew whether or not event horizons really existed. And it turns out that not only do they exist, but they agree with Einstein's theory of general relativity. Everything in this picture is in agreement with what was expected, including the fact that this disk here, so this is the accretion disk around the black hole, it's brighter down here than it is up here because the gas and the stars are moving so fast that space and time are bent. And so this gas is relativistically beamed. The emission from this gas is relativistically beamed towards us. So this part's coming towards us and this part's coming away. Okay? And the fact that this is a real image is incredible. So to give you a sense of how big this image is, right? How big this black hole is. Here's someone who put a sketch. I mean, the memes on this thing are amazing, right? But this is a size comparison between this black hole event horizon and the size of our solar system. Okay, so the sun is way in here. This is Pluto's orbit. Here's Voyager 1. This is about where Voyager 1 is. So basically, with this telescope, the Event Horizon Telescope, we've taken an image of something the size of the solar system at 55 million light years away. Okay, it's incredible. And what you get when you have interferometers is that resolution, right? Because you can mimic a really big bucket without having to build a really big bucket. So this black hole has a name. It was given a name by a Hawaiian scholar, Poeki. It means, so it's in the Hawaiian language, it means embellished dark source of unending creation. And the reason why it has a Hawaiian name is that one of the telescopes that was used was in Hawaii. And you might know that the summit of Mauna Kea is a sacred site to Native Hawaiians. And so that's why you might see a lot of astronomical objects being named in that language. And the sign that you really made it big is that you have a limerick made up. Okay, and so this emerged pretty fast. Astronomers reveled in bliss at seeing a wonder like this, the fires of heaven in M87, within them the darkest abyss. So we can use this technique of interferometry to give us images that have really high resolution. And generally, right about now, if you want a really sensitive picture, you would build a one big dish. And if you want a lot of resolution, you'd build a lot of little dishes very far apart. But in the future, what we're going to want is both. Okay, we want our cake and eat it. We want to be able to have our cake and eat it too, right? So we want both sensitivity and resolution. And so the future, at least at frequencies or wavelengths around a centimeter, is called the square kilometre array. And so this is an artist's impression of the square kilometre array. And so it's a telescope that has some telescopes in Australia and some of them in South Africa. Headquarters is in the UK. And all of these lines shows all of the light that's recorded by these telescopes that's being beamed all over the world. So here's an artist's impression of the square kilometre array in South Africa. And so what we do is get collecting areas, we put a lot of these radio telescopes, thousands of radio telescopes on the ground, and then we multiply the signals for each one of these radio telescopes together, so we get both sensitivity and resolution. And so the Square Kilometre Array is a project that has been going on for a couple of decades now. The design is fairly mature. We're going to have these antenna-like things that operate at low frequencies in Western Australia, and then we're going to have dishes that operate at slightly higher radio frequencies in South Africa. And the design is set, the number of dishes is also set, and in fact there are already some of these dishes here on the ground. Okay? And so in the next decade or so, we're going to build this fabulous new radio telescope. And this fabulous new radio telescope is going to do all sorts of science. So I told you about black holes today, but it turns out that radio telescopes can tackle all sorts of outstanding questions, ranging from general relativity to the very first galaxies, to how galaxies evolve, to what the universe looks like, to how planets and molecules and life form, to what the magnetic fields of the universe are doing, and of course the things that we'll see in the universe when we've looked at the universe in a different way for the first time. Okay? And this, past practice shows, is always the coolest thing that you find. Okay, so the reason to build telescopes, the reason you always justify the telescope with this stuff, but the reason you wind up building it is this stuff. And so the Square Kilometre Array is going to have the broadest range of science of any facility worldwide. And so here are the worldwide partners for the Square Kilometre Array. And so you'll notice Canada is colored in light blue here. We are a founding member of the Square Kilometre Array, and I am the Square Kilometre Array Science Director for Canada. And so if all goes well, this telescope will begin construction in a couple of years. The hope is that Canada will build a correlator for this machine. We have some prototype designs, and in fact we've been leading the consortium to design that. We also have scientists all around Canada that have expertise in almost every science field that the Square Kilometre Array will tackle. So I'll leave you with this. The Square Kilometre Array is becoming a reality, and Canadians are deeply involved, which means I'm going to have a job for a long time. There are exciting times ahead for radio astronomy, so stay tuned. Thanks.
questions from the audience. We've got a runner here with a microphone. Oh, yeah, there you go.
So closest first.
I apologize if this brings up some topics that are a little tricky for you to handle right now, but have you considered some factors that would inhibit the development of the radio telescope there, such as international politics, ownership rights, earthquakes and disasters in areas to maintain the complex instruments and materials that you have there, or even meteorological factors that might inhibit immediate results?
Yep. So it turns out that in meteorological factors at these frequencies are a little bit less of a concern, because at these frequencies, the frequencies that the SKA operates at in particular, the atmosphere is largely transparent. So this is the kind of telescope that you can observe in the rain and through the clouds. So meteorologically, there's a little bit less of a concern. In fact, the biggest concern for this kind of telescope is radio frequency interference. So I mentioned that all of our cell phones have antennas in them. That's because there are constellations of satellites that are beaming radio signals toward the Earth. And so there are actually pieces of the universe in frequency space that are inaccessible to astronomers on the surface of the Earth because we now have such a widespread global network. Your other question was about international politics. Certainly a project like this that has many, many international partners in many different parts of the world where the standards of living are very different. That's a huge concern. It's one of the reasons why a telescope like this takes a long time to build. There's been a lot of negotiation on all sides and with all countries to make sure that this is benefiting not only astronomers, but the people in the places where these telescopes are being built, as well as the people in the places whose governments are contributing to this kind of money. So this is definitely on our radar. It's something that's taken very seriously by the astronomical community, and it's something I'd be happy to talk to you more about. So the short answer to your question is yes.
Thank you. That actually answered a second question I had about how the information from this would be applied. Thank you.
Just over here.
Is there any talk about establishing a telescope on the moon or other planets now?
So the question was, is there any talk about establishing a telescope on the moon? And the answer is right now it's still too expensive. So if you were on the moon, there are a lot of advantages. It's much darker. There are no cell phone towers. It would be great. But as you've seen from this talk, radio telescopes tend to be quite large. And so you'd have to blast all of that up into space and then set it up on the moon. And right now the launch costs are so high that generally speaking, anything that you can do from the ground, you do from the ground. So because our atmosphere is transparent to radio waves, I've not heard a lot of talk about space radio wave missions. Now, if launches became much cheaper and we had a mechanism for operating easily on the moon, then that calculus might change a little bit. But so far, we're going to keep our radio telescopes on the ground.
All right, we have one last question. Would you like to ask your mom a question?
Why did they use a black hole that's so far away? Why couldn't they just use the one that's in the middle of our galaxy?
That is a good question. So the only, I'm going to get this all night. You don't understand the number of questions from this kid I answer. So the reason actually why, so there's only two black holes that it is possible to observe from the surface of the Earth. One of them is the one I showed you, and the other one is the black hole at the center of our galaxy. And the reason why they observed this one and not the black hole at the center of our galaxy is that they're up at different times of day. And the times of day when our galaxy was overhead, it was cloudy on the surface of the Earth. So I just said that radio telescopes can see through the clouds. That's true for a telescope like the Square Kilometre Array, where the wavelengths are centimeters in size. But the telescopes that were used to make the picture of the black hole actually observe millimeter scale waves. And so you have to have an atmosphere that's you have to have an atmosphere that's clear. There can't be any clouds in the sky. And so in order to get that picture that I showed you, there needed to be like a minor meteorological miracle, because it had to be clear across the whole surface of the Earth for a period of several days. So the astronomers had actually blocked off a week to try to get those observations, and unbelievably it was clear for 4 straight days, and so they were able to observe for about 4 straight days. So the reason actually is the weather. That's the next target. That's the next thing the Event Horizon Telescope will do.
Could I have one last question? The James Webb telescope, first of all, how does that relate to you and your role in Canada and us as Canadians? And secondly, how does it relate to the SKA?
Sure.
Relative to that?
Yeah, so the James Webb Space Telescope, for people who don't know, is the successor to the Hubble Space Telescope. I showed a lot of HST images in my talk. And so the reason for going above the atmosphere is that the atmosphere has a tendency to blur images. So that for the astronomers and the amateur astronomers in the room, you might have heard of atmospheric seeing. So you get away from that when you go up into the atmosphere. Now the James Webb Space Telescope is the successor to Hubble, but it's actually going to observe at slightly longer wavelengths in the infrared. That's going to allow it to look deeper into the universe because it has a much bigger mirror. And it's also going to allow us to look at things like protoplanetary systems. So one of its major science goals is trying to understand how planets form. So the Canadian government has invested over $150 million in the James Webb Space Telescope. We actually built the Kilometre system as well as one instrument. This is the largest single investment in space astronomy that has been made by the Canadian government. That investment was made 2 years ago. So Canadians will get about 5% of the observing time on JWST. That doesn't sound like a lot until you remember that Canada is 10 times smaller than the US, okay? So it's a lot of time. And the JWST is $1 billion instrument, a several $billion instrument that's in the class of world observatories. It's an observatory that's expected to revolutionize the way that we see the universe. And the SKA is another world observatory, except at a different frequency. It's got around the same price tag. It's divided between all of these partners. And because it's on the ground, we're expecting it to work for decades. But in the same, along the lines of the JWST, the SKA should revolutionize how we're able to look at the universe. So they're very complementary is the short answer to your question.
Cool. All right, let's thank Kristine again for an amazing talk.